All right, we're back for Monday lecture, Physics 1151. We're finishing up chapter 19 today. Heat transfer mechanisms. We covered conduction and convection last Thursday. We're going to get into radiation today, and then we're going to summarize the chapter after that. So, we've talked about various energy transfer mechanisms and sources of energy, but so far we still have yet to cover the most important energy source for the Earth and the atmosphere, and that is our sun. The sun heats up the Earth and the atmosphere during the daytime, and the Earth cools down at night when there is no sunlight. So, how is this energy transferred from the sun to the earth? Well, is it conduction? Well, no. Conduction requires that the two bodies be in physical contact with one another. We're not in physical contact with the sun. So, the sun's energy cannot be transferred via conduction. Is it convection? Well, what's convection? Convection is the transfer of heat due to the bulk motion of a fluid. Well, it's mostly vacuum between the Earth and the Sun, so it can't be convection. It turns out that the Sun's energy is transferred by electromagnetic radiation or electromagnetic waves. And every body, the Sun, the Earth's surface, the atmosphere, each of us, emits electromagnetic radiation. Now, the amount of this radiation that a body emits depends primarily on temperature, we'll see in a bit, and it also depends on the color of the surface. And here's an example. So you have sunlight, and the sun strikes a dark surface, a black surface, and over here to the right, it strikes a highly reflecting surface. So absorbing, reflecting. Okay. The black surface will absorb almost all the sunlight, for a perfect black body, all of the sunlight incident upon it, and it will heat up more than the reflective surface, which reflects most of the radiation. So the amount of radiation absorbed, and it turns out that a good absorber of radiation is also a good emitter of radiation, so the amount of radiation emitted or absorbed by a surface at a given temperature depends on how dark it is, or on the other extreme, how reflective it is. Right? Reflective surfaces are poor absorbers and they're poor emitters. And a material that absorbs completely is called a black body. Black is absorbing. So mathematically, if we know the temperature of a body, we can calculate the power, the heat per time radiated by the body. It goes as temperature to the fourth power. We'll get into these other constants in a minute, where this is called the Stefan-Boltzmann equation. Now, to use this equation, we have to remember to use absolute temperature, so that means the temperature has to be in units of Kelvin. So what are these other variables? Well, A is the surface area of the body. Sigma is just a constant, which we call the Stefan-Boltzmann constant. And epsilon, this E-looking thing, is the emissivity of a body. And basically, it's a measure of how good the body is at radiating at a given temperature. And so the emissivity is 1 for a black body, and it's close to 0 for bodies that are highly reflective. So it's based on the color of the surface, and it's just a constant between 0 and 1. So the primary variables influencing how much energy is radiated by a body is temperature, followed by surface color. So if we want to calculate, each of us radiate power. We radiate energy, and we'll do a homework problem. You can plug in our body temperature, which is about 310 Kelvin, and calculate it. But we also absorb energy, heat, due to radiation by our surroundings, the atmosphere. And so we can calculate the net power, what we emit minus what we absorb, if we know our body temperature and if we know the temperature of the surroundings, and we apply the Stefan-Boltzmann for each of those terms. And if we collect these terms, the net power that we radiate depends primarily on the temperature difference between us and our surroundings. One little tidbit that's not going to be important in the course, but in practical calculations, is that if the sun's rays strike us at some angle theta, you have to multiply this Stefan-Boltzmann equation by theta. So let's do an example here. Okay, let's assume that the sun radiates energy, the same amount of energy and the same wavelengths as a black body with temperature of 5700 Kelvin. So the sun you can approximate as a black body at a temperature of 5700 Kelvin. And let's approximate a campfire here as having a temperature of 800 Kelvin. So if we assume that each body has an emissivity close to 1, then calculate the ratio. How much of the amount of energy per area emitted by the sun divided by the energy per area radiated by the campfire. So the sun is 7 times hotter. Let's see how many more times it radiates than the campfire. Okay, stop your camera, calculate. Okay. So we're back. We can divide. We use the Planck equation, and we write down the equation for the sun. Power radiated is the heat per time, energy per time. We can divide by the area since we're trying to calculate power per area. And we can do the same for the fire. And remember, as with all ratio problems, we write down the equation for the sun divided by the equation for the this should be fire, T-fire, I'm sorry, typo. It's corrected here. And the constants cancel. If the emissivities are both 1, they cancel. And the ratio of the power per area of the sun divided by the fire is just the ratio of the two temperatures to the 4th power. And so this is interesting. The sun is 7 times hotter than the campfire, but it radiates, each meter square radiates 2,580 times more power than the campfire. Okay, and that's because the power per area radiated goes as temperature to the 4th power. Okay? So every time you double the temperature, you radiate 2 to the 4, which is 16 times more radiation. Okay? And so the sun radiates much more than the campfire. And you should be able to do these ratio problems on an exam. So there's several applications that make use of radiation, and I have a infrared thermometer here, sorry, and I'm going to take my temperature. Okay. (97.9 degrees Fahrenheit). Okay. How does this work? Well, remember that each of us radiate electromagnetic energy, heat, and it's proportional to the 4th power of the temperature. And so by knowledge of the amount of energy that is radiated by my forehead, the temperature can be calculated. Now, the caveat here is if we go back to this equation here, all of these devices that use the radiated power to measure temperature have to make an assumption on the emissivity of the body. In this case, it's the skin. And so if the approximation for emissivity is a little different than the actual emissivity of a given surface, in this case my skin, you're going to get errors in converting the amount of radiated power to the temperature. And so these can have some errors. If they're well calibrated, they're usually pretty good. Here's some example of a thermal imager, okay? And these are used to map temperature differences across a scene. Okay, so here you have a scene. You have some guy getting into his car, trees in the background and the buildings. And each part of the scene could be at a slightly different or significantly different temperature. Okay, so it's different parts of the scene at different temperatures, remember, are going to radiate different amounts of electromagnetic energy. So if you have a camera here with a lens, and that lens forms an image of the scene onto an infrared detector, that detector, with processing, each pixel, the amount of energy hitting each pixel of the camera is proportional to the amount of radiation from the corresponding part of the scene, which is proportional to temperature, to the fourth power. And so what we're doing here is we're creating a temperature map by measuring the amount of power radiated from the different parts of the scene. And that can get converted by signal processing circuitry and software, and we represent different amounts of radiation as different levels of grayscale if it's a grayscale image, or as different colors if it's a color image. So basically this is all fancy jargon for saying that we're creating a temperature map of the scene which is viewed as an image. And here's some more examples. Basically, again, this is just a heat map of a scene. Here's for body temperature measurements. These are being used now, especially with COVID now, to detect people with fevers. So again, if you have a fever, you're going to be at a higher temperature. You're going to emit more infrared radiation, and the thermal imager here, or just a simple infrared thermometer, can use that amount of radiation to get temperature. So this method is being used all over right now with COVID. It does have a few potential flaws. We talked about the first one already. Remember, the it makes some assumption of emissivity to calculate temperature from radiation. And so different surface colors could deviate slightly from an assumed emissivity, and you can get small errors in the temperature measurement. The other thing is it's measuring a surface temperature, and it doesn't take into, as opposed to a core temperature. And so it's not, it doesn't take into account higher temperatures caused by exercise or stress. Okay, so for example, if you're running to catch a flight through the airport and you're sweating and your skin temperature has increased, that can be interpreted as a higher body temperature, okay? Remember, this is measuring surface temperature, which is the temperature of your skin. And then the other complication is that it's not just you or I that's emitting radiation, but everything in the background is. And so if your camera, your infrared thermometer is getting radiation from different parts of the scene other than your forehead, maybe the surroundings, that can complicate the temperature measurement. So nevertheless, it's a non-intrusive, it's a non-invasive method for measuring temperature, and it does a reasonably good job within the assumptions, and so it's used quite a bit. Um, Here's another example, temperature map of your house. Okay, this is using a thermal camera. And this can be used by firefighters to determine where the fire is, the temperature at the various parts of the house. It can also be used to detect heat loss. Okay, so on these maps, higher temperatures are typically represented by warmer colors, your red, your yellow, and lower temperatures are typically represented by cooler colors, your blues and your violets. And so we can see here that there's heat being lost through the roof, through the windows, through the base. And so these can be used to determine how to better insulate the house or where the heat loss is. It can also be used for fires. It can be used for identifying short circuits, right? It's gonna be warmer. And so these temperature maps are extremely useful in a variety of fields. One last example is using it to detect tumors, right? Warmer areas. So these temperature maps can be used for that. So there's a pretty good bet that for most of you, you will encounter in your job or in some area of your life, you will be using these infra or thermal imagers, and most of us use these infrared thermometers. So it's important to have a little bit of a background, a basic background in thermal radiation. So one last question. So the sun, how does the sun heat up the earth? Okay, well, the sun emits primarily shortwave radiation, which is in the visible, and that heats up the surface of the earth, and the surface of the earth radiates. So why don't we see the radiation emitted by the surface of the earth? Okay, well, it turns out that most of the Earth's radiation that we emit, or that any body at Earth-like temperatures emits, is longer wavelengths. In other words, it's infrared radiation. So it turns out that the peak wavelength emitted by a body gets shorter as the temperature increases. So the sun emits primarily in the visible and the surrounding regions, the near infrared and the ultraviolet, whereas at our body temperatures, most of our energy is emitted in the infrared. And so that's why you don't see the radiation emitted by you or I or any object at Earth-like temperatures unless we use a camera with infrared detectors like these thermal imagers. So let's kind of summarize here the three mechanisms that we discuss for heat transfer, because on the exam it's important that you understand not only the equations, but that you understand when each mechanism is the dominant mechanism of heat transfer and the general physics of each. So remember, conduction, two objects have to be in physical contact in order to get heat transfer by conduction. Okay? And it arises due to a temperature difference between these 2 points in contact. And we go back to the example of the metal straw that I put into the water last night, right? That the energy was transferred from the hot water to my hand by contact with the metal straw. Okay, so you have to be in contact. Okay, and this is the predominant mechanism of heat transfer in most solids. So, but not liquids or gases. And then we had the equation for conduction. So if I want to calculate the heat per time, the energy per time radiated, It depends on the conductivity of the material, right? Metals, better conduction, wood and air and most gases, poor conduction. Depends on the area of the body, depends on the temperature difference between the two bodies, and it's inversely proportional to the gap between the two bodies. Now, often when you buy insulation, you might see these things called R values, like R11 or R15 insulation. What that typically is the R value is equal to the thickness, L, divided by the conductivity. And so I'm expressing in this particular case here, we can write the energy per time radiated in terms of the thermal resistance, and this is a useful form in some cases. We talked about convection, right? Convection is the predominant transfer of heat in a fluid, and like air, water, liquids, gases, and that's just due to the large-scale motion of the fluid, okay? And that was due, remember again, to the density differences due to different temperatures, and that gives rise to buoyancy, which mixes the air and it transfers the heat. So convection is the primary mechanism for fluids. And then the last method that we just described was heat transfer by radiation, and that was due to electromagnetic waves emitted. And we can calculate the power radiated if we know the surface temperature more accurately. And we can calculate the power absorbed by our body if we know the temperature of the surrounding air, the surroundings, and that gives us the net power that we radiate, right? What we emit minus what we absorb is the net power that we radiate. And so the main point with radiation is that you don't need a medium. You don't need a fluid. We don't need a solid. Electromagnetic waves can be transferred without a medium in vacuum or a medium. So they can be they don't need any medium for transfer. So it's important to understand the differences between the mechanisms, how energy is transferred for each, the mathematical equations if given, and you should be able to do not only calculations, but you should be able to do ratio problems. Like on an exam, if I double the temperature, by how much does the power emitted by a body increase? Or with conduction, if the second body has twice the area and a quarter of the length of the gap thickness, what's the ratio of the power emitted by the two bodies due to conduction? So you should be able to do those. And so that pretty much is it for chapter 19. Spend a few minutes just going back over a few of the main points. It doesn't hurt to repeat it one more time. So after we defined work and we defined heat, and we calculated work for various cases, right? It's the integral of P dV, right? For the force times displacement. And so if we're able to calculate the external work done on a body, we call it W external. Your author just calls it W, but what he means is it's the external work done by the body on the system. That the external work done on the body plus the heat added to the body give rise to the change in the thermal energy of the body, if we can neglect macroscopic motion of the body. And this is the first law of thermodynamics. So we spent quite a bit of time on this. It definitely should be on your exam cheat sheet. And so the work done and the heat added depend on the process by which the system is changed, whether it's adiabatic, isochoric. So you should be able to calculate work and heat for those different cases. and understand the sign conventions. Remember, if positive work is done by the system, for example, compressing a gas, that's positive W, right? The force done by the system is in the same direction as displacement, and so external work is positive. If a gas expands, or the volume expands, then the external work done is negative because the displacement and the external force are in the opposite directions. So positive work is done in compressing, negative work is done in expanding, external work. If heat is added to the system, Q is a positive number. If heat is removed from the system, Q is a negative number. Okay, so these sign conventions are important. The sum of the work, both work done on a body, mechanical work, and heat added due to temperature differences, they both can raise the thermal energy of the body. Remember, and the thermal energy just depends on temperature, and that's the measure of the microscopic energy of the molecules due to kinetic energy and potential energy. So work done on a body and heat added give rise to changes in the thermal energy. So that's the first law of thermodynamics. Go back and look at that for several different processes, the adiabatic, the isochoric. You should be able to solve problems for each of those cases. Some other concepts, we went over work. The work done on a gas. Okay, well, we take the area under the curve, the PV curve, and if I is the initial state, V is the final state, and the process goes from I to F along this curve. We calculate the area under the curve, PdV, and the external work is the negative of that area. Okay, and so as an example, in this case, dV is what? dV is positive, right? Because V final is greater than V initial. And so what this means is the gas is expanding and the external work is negative. So you should be able to calculate work done given a PV curve or given the process. And then apply that to the first law of thermodynamics. We solved some calorimetry problems, and you'll be doing that in the lab shortly if you haven't done it already. I think it's this next week. And so this was a method used to determine the specific heat capacity of a solid, right? We insulate it inside a container. For example, a beaker of water surrounded by styrofoam so no heat can enter. And in that case, if we call the system the water plus the beaker plus the solid whose heat capacity we're measuring, the sum of the heat added to each of them has to add up to be 0 because no heat enters or leaves the system. And so then the heat lost by, for example, the heated metal was the heat gained by the water in the cup, and we can, if we know the temperatures of each at the beginning and the temperatures at the end and the masses, we can calculate the specific heat. So that's calorimetry. We did PV curves for various processes, adiabatic. We did it for isothermal. We did it for isochoric, isobaric. You should be able to understand these PV diagrams on an exam. So another thing to study. We discussed specific heat capacity, which if you remember, that little c if we're using mass and a big C if instead of mass we're using moles. And so the specific heat capacity is just how much heat needs to be added or removed from the system to change 1 kilogram of mass by 1 degree Celsius. And so a bigger number for heat capacity means more thermal inertia. Like it's harder to heat or cool that substance. A small number means it's easier to cool and heat. And I go back again to the example with the pizza and the crust. If you take the pizza out of the oven, you're going to burn your tongue on the cheese before you burn your tongue on the crust, in part because heat is retained more by the cheese than it is the crust. It has a higher heat capacity. It also has something to do with the difference in the thermal conductivities, but it also is related to the difference in heat capacities. We discussed that for an ideal gas, the specific heat depends on the process, right? It's greater for processes at constant pressure than it is at constant volume. So go back and review that. We discussed latent heat, which is the heat that enters or leaves a substance in order to change its phase. And think again about the boiling of water on the burner, right? The energy from the burner was used to heat the water and to evaporate the water, and it took a lot more energy to change the phase of the water than it did the temperature the water. So you should be able to do problems where you can calculate the amount of heat needed to raise the temperature of a substance from a given temperature to a final. And some of that heat could also, if you cross, like for example, 0 or 100 degrees C for water, some of that energy you have to calculate due to the latent heat. And then finally, today we discussed the three primary mechanisms for transferring heat, which are conduction, convection, and radiation. So there's a lot of stuff in this chapter. So take some time to go over it. There's some more worked examples I did here on heat transfer. This should obviously be examples 2, 3, and 4. Typo. Work through these, and let's talk about them during Tuesday or Monday's synchronous class meeting if there's any questions. But you should work these through. You should go through the chapter and the examples, and you should work up homework problems. Right. So go through these examples. Stop by if you have any questions. Other than that, that's it for today. So have a good day.